Hi everyone, welcome back to Swift Academy. As you can see, we have our third set of 10 essential Swift interview questions ready to go. If you watched our first two videos, you know we don't just memorize dry definitions. We look at exactly how Swift operates under the hood. In Part 1 and Part 2, we mastered the core fundamentals, unlocked syntax shortcuts like trailing closures, and traced how memory is allocated on the heap using automatic reference counting to stop retained cycles. Today, we are taking it a step further. We're going to break down complex memory mutations using the inout parameter, untangle the difference between capitalized self and lowercase self, master delegation patterns, and dive deep into generics and memory references like weak versus unowned. By the end of this video, you'll be ready to clear your next technical round with total confidence. Let's jump straight into question number 1. When is a set more preferable than an array in iOS Swift? You should choose a set if your collection meets 3 specific rules. First, you need no duplicates, meaning you only care about unique items. Second, you want no order. The sequence of the elements doesn't matter to your application logic. And third, you are storing hashable types like strings or integers. The ultimate reason to make this switch comes down to the performance difference. If you search an array using .contains, it is a slow O(n) operation because Swift has to check items one by one from top to bottom. The more items you have, the more time it takes. A set, however, is instant O(1). It uses a hash key to jump directly to the item, meaning it takes the exact same instant speed whether you have 10 items or 1 million items. Let's look at how this works in actual code. First, notice the array representation. It safely maintains the order, but it allows duplicates, so printing it keeps both instances of the string read. Now look at the set representation below it. When we initialize it with the exact same values, Swift automatically drops the duplicate read and stores the rest completely unordered. This brings us to the big performance win at the bottom. When we call setBackgrounds.contains read, Swift doesn't scan through a list. It hashes the value and locates it instantly in O(1) constant time. Mentioning this optimization is exactly how you impress an interviewer. Moving on to our next interview question. How do we show the use of the lowercase self keyword in a method using a practical example? To explain it simply, self is a special implicit property in Swift that acts as an instance reference, meaning it points directly to the current runtime instance of your type. As for its common location, you'll almost always see it implemented inside initializers or methods of a class, struct, or enumeration. This brings us to the main purpose, clearing up name confusion. We use self to tell Swift the difference between the variable that belongs to the whole object and the parameter being passed into the function when they have the exact same name. Let's take a look at the code structure on the right to see exactly how this solves name clashing. Inside our student struct, we've declared 2 internal properties, my name and my friend. Notice what happens inside our init block. The incoming argument names match our property names perfectly. Without self, if we just wrote my name equals my name, the compiler would get confused by the name overlap. By prefixing it with self.myname, we explicitly tell Swift, take the value from the incoming method argument on the right, and safely assign it to our object's property on the left. Highlighting this exact behavior proves to an interviewer that you understand clean code organization. Let's move on to question number 3. What is the difference between capital self and lowercase self in Swift? This is a very common question when dealing with protocols. Let's break it down. First, capital self refers to the type. Specifically, it acts as a dynamic placeholder for whatever data type actually conforms to the protocol. That could be a built-in type like an int or string, or it could be your own custom struct. Because it represents the type itself, you will mostly see capital self used as a return type in your method declarations. On the flip side, we have lowercase self, which refers to the value. Instead of representing the blueprint or the type, lowercase self refers to the actual value or instance stored inside that type at runtime. For example, the actual number 4, the specific string hello, or a unique object you just initialized. You will use lowercase self inside your methods when you need to perform actual operations on that specific piece of data. Let's tie it all together with a code example so you can see them side by side. Look at the square integer protocol at the top. The square function returns capital self. This tells the compiler, whatever type adopts this protocol, make sure it returns that exact same type. Now look at the extension below where int adopts the protocol. Inside the function body, we return lowercase self multiply by self. Here, self represents the actual number we are operating on. So, when we define our number as 4 and call number.square, the capital self guarantees an int is returned, and the lowercase self does the math of 4 multiplied by 4 to give us our final result of 16. Explaining it this way shows the interviewer you completely understand the difference between a type and a value. Moving on to question number 4. How can we use the inout parameter in iOS Swift? Let's explain this with an example. First, let's understand exactly what an inout parameter actually is. Normally, when you pass a value into a function, it is completely locked as a constant. You cannot change its value inside the function. But if you add the inout keyword, it lets you modify a value type like a struct directly inside the function. By the way, if you want to know more about how we use the mutating keyword to change structs, I explained that simply in our iOS interview questions part 2 video. Be sure to check that out. There is one important rule. When you pass your variable into the function, you have to put an ampersand or an and symbol in front of it. This tells Swift that the value is going to change. Now, let's look at why this is so helpful for your app's memory and performance. Without inout, things can be slow. Swift has to make a full copy of your struct when it enters the function, and another full copy when it returns. This wastes a lot of memory, especially for large structs. With inout, it is very fast. Swift modifies the original memory directly. There are no extra copies made, which makes it perfect for saving memory when working with heavy structs. Let's take a look at a quick code example to see exactly how we write this out in Swift. At the top, we have a simple struct called myStruct. Below that is our memory saving function. Notice we put the inout keyword right inside the parameter list. This tells Swift we want to modify the original struct, not a copy. Finally, look at the very bottom. When we call the function, we place the ampersand symbol right in front of our variable. This passes the direct reference, updating our data safely and instantly with zero memory waste. Let's move on to question number 5. State your understanding of delegates in iOS Swift. To understand the delegate pattern, you just need to know its 3 main parts. First is the protocol. Think of this as the rules. It is simply a list of tasks or messages that define what needs to be done, but it doesn't actually say how to do it. Second is the delegator, which is our sender. This is the class that has a job to do or an event to report, like a network manager finishing a download. It is important to note that the sender holds a weak reference to its helper. Third is the delegate itself, which acts as the receiver. This is the class, like a view controller, that signs the protocol contract and provides the actual code to do the work when the event happens. Now, let's look at a clear code example to see how these 3 pieces connect. First, we will put the setup for our sender on the left, and we will put the setup for our receiver on the right. Looking at the sender setup on the left, step 1 is defining our rules in the task delegate protocol. In step 2, inside our data manager, we create a weak variable for our delegate. When the data finishes fetching, the manager simply calls delegate. Task did finish to pass the success message along. Finally, look at the receiver on the right. Our profile view controller adopts the protocol. Inside the init method, it assigns itself as the helper by saying manager.delegate equals self. Then, it provides the actual code for the task did finish function to print and update the UI. Now, here's a quick question for you all watching. Notice that we use the keyword weak for our delegate variable on the left side. Do you know why this specific keyword is absolutely necessary in Swift to protect our app? Drop your answers in the comments below. Let's dive into the next interview question. What do you understand about optionals in iOS Swift, and exactly what problem do they solve? To understand the solution, we first need to look at the old problem back in Objective-C. In the past, only reference types like objects could be empty or nil. Simple value types like integers or floats could never be empty. They always had to hold an actual number. Here is the Swift solution. Optionals completely fix this issue. They allow absolutely any type of variable, whether it is text, a number, or an object, to safely and completely lack a value. To understand the concept, just think of an optional as a simple delivery box. That box can either contain a valid item inside, or it can be completely empty, which we call nil. Let's look at the code on the right to see this in action. First, we create a variable called text. Adding that question mark tells Swift it is an optional. At this point, the box starts completely empty or nil. Next, we put a valid string inside the box. I will go to school. Finally, when we print it, Swift knows the box has something inside. Now, here's a quick question for you watching. If we want to safely take the text out of this optional box, what common Swift technique do we use? Let me know your favorite way to unwrap optionals in the comments below. Let's move on to question number 7. How can the double question mark symbol be used in iOS Swift programming? First, what is it actually called? The double question mark symbol is officially known in Swift as the Nil Coalescing Operator. You can think of this operator as a safety net. It is used to give an optional variable a safe, default fallback value just in case it turns out to be empty. Here is exactly how it works. It looks inside the box, which is your variable. If there is a real value inside, it goes ahead and uses it. But if the box is empty, meaning it is nil, it safely uses the default value you provide instead. Ultimately, this is a fantastic, clean shortcut. It is a much faster and cleaner way to check for nil without writing long, messy if-else statements. Let's see this in action with a code example. On the right, let's say we have a variable named number that is an optional integer, and right now it is completely empty or nil. Below that, we use the double question mark. Checks number. Since number is empty, it safely falls back and gives num the value of 0. So, when we print it out, the result is safely 0. Now, a quick question for you watching. What would num print out if number was set to 5 instead of nil? Let me know your answers in the comments below. Moving on to question number 8. What is the meaning of a guard statement, and what are the advantages of using the Swift guard statement? To understand the meaning, think of the guard statement as the bouncer of your function. Checks if a condition is true right at the very start. If that condition fails, it immediately kicks you out of the function. This brings us to its first big advantage. The early exit. It forces you to handle any errors or missing data at the very top. By dealing with the bad stuff first, it keeps the rest of your code clean, flat, and safe. The next huge advantage is safe unwrapping. Unlike a regular if statement, when a guard safely unwraps an optional, that new variable becomes fully available for you to use for the rest of the entire function. Let's look at the code on the right to see exactly how this works. We have a function called greetUser that takes an optional name. In step 1, our bouncer uses guard let to check if that optional name has a real value. Moving to step 2, if it is completely empty, it prints an error and uses the return keyword to exit immediately. Finally, in step 3, if it does have a value, we can safely use that unwrapped valid name variable down below without our app crashing. Let's move on to question number 9. What do you understand about generics in iOS Swift? First, let's look at the problem, which is code duplication. Normally, if you write a function to compare two integers, you have to write a completely duplicate, clone, function just to compare two strings. To fix this, we have the generic solution. Generics let you write a single, flexible function that can accept any data type, avoiding repetitive code entirely. Generics can be used seamlessly with functions, classes, and structures. How do they work? By using a placeholder. We use a letter like T inside angle brackets to act as a placeholder for the type. Swift figures out the actual type, like an integer or a string, automatically when you run the code. Now, let's look at a code example to see exactly how this works in practice. First, we will set up the old way, which involves code duplication, on the left side. Then we will set up the clean, generic way on the right side. Looking at the old way on the left, you can see Swift's strict type safety actually working against us. Because that first function explicitly demands integers, we cannot pass text into it without the compiler throwing an error. To get around this, developers often copy and paste the exact same logic just to change the word int to string. This violates the don't repeat yourself principle, making our code bulky and much harder to maintain if we ever need to change the logic later. On the right side, the generic approach solves this perfectly without losing compiler safety. The letter T, inside the angle brackets, acts as a placeholder. Notice that we also added a constraint called equatable. This tells Swift to only allow data types that actually support being compared with an equal sign. Because we use that exact same T for both parameters, Swift strictly enforces that input A and input B must be the same type. Under the hood, Swift looks at our inputs and automatically replaces the T with an integer or a string during compilation, giving us one clean, crash-free function. Now, here's a quick question for you. Can you name a popular built-in Swift collection type, like an array, that heavily relies on generics under the hood? Drop your answers in the comments below. Let's move on to question number 10. How should one consider the usage of strong, weak, and unowned references in Swift? To manage memory safely, Swift uses 3 types of references. The first is the strong reference. This is the default way Swift keeps objects alive in memory. Second, we have weak references. These are used to break retain cycles safely by working with optionals. By the way, if you want a complete step-by-step masterclass on spotting and fixing retain cycles, make sure to watch our previous video titled, Why Strong Reference Cycles Destroy iOS Performance. The link is right there in the description below. And third, we have unowned references. These are specifically for parent-child relationships where the child will never outlive the parent. Let's take a deep dive into strong references to see exactly how they work. By default, whenever you create a property or a variable in Swift, the compiler automatically makes it a strong reference unless you explicitly tell it otherwise. You can think of a strong reference as a protector. Its only job is to protect an object from being deleted. As long as there is at least one strong reference pointing to an object, that object stays alive in memory. However, there is a danger. If two objects hold strong references to each other, they get trapped and can never be deleted. This creates a nasty memory leak known as a retain cycle. Look at the code on the right. When we create Alice, we have one strong reference. When we point person 2 to Alice, we now have 2. Even if we set person 1 to nil, Alice stays alive in memory because person 2 is still holding a strong reference, preventing the instance from deallocating safely. Now, let's move on to weak references and see how they act as the ultimate cycle breakers. Unlike a strong reference, a weak reference acts simply as an observer. It points directly to an object, but it does not protect that object from being deleted by the system. This brings us to automatic nil allocation. If the object a weak reference points to gets deleted from memory, the weak reference is smart enough to automatically turn itself into nil. Because it needs the flexibility to become nil at any point during runtime, a weak reference must always be declared as a mutable, optional variable using weak var. In terms of common use cases, weak references are heavily used in iOS delegate patterns and closure capture lists to keep our classes decoupled and entirely prevent memory leaks. Let's look at the code structure on the right. Inside our apartment class, we mark our tenant property as weak. We instantiate Alice and unit 4a as optionals and build a link. The moment we set Alice equals nil, there are 0 strong references remaining to that person instance, so it deallocates completely. Because it was a weak property, unit 4a.tenant automatically transitions to nil, freeing our system memory cleanly and safely. Now, a quick question for you watching. Since we know weak references must be optionals, what is the main functional difference between a weak reference and an unowned reference? Let me know your answers in the comments below. Finally, let's talk about our third category, unowned references. In one way, they are very similar to weak references. Just like weak references, unowned references do not protect an object from being deleted. However, there is a major difference. They are never optional. Unlike weak references, unowned references assume the object will always be there. Because of this, they are not optionals. Because they are not optional, there is a serious risk involved. If you make a mistake and try to access an unowned reference after the object has been deleted, your app will immediately crash. Therefore, the common use case for unowned references is very specific. They should only be used when you are 100% certain that the referenced object will outlive the referring object. Let's look at the code example on the right to see when this makes sense. We have a city class, and inside we mark the country property as unowned. A city cannot physically exist without a country. Because we are 100% sure the country will always exist as long as the city does, it is perfectly safe to use unowned here. To wrap this all up, let's look at a quick memory management summary. Here is a comparison table that breaks down strong, weak, and unowned references so you know exactly when to use each one. Starting with strong references. Do they keep an object alive? Yes, they absolutely do. For weak references, do they keep it alive? No. And for unowned references, do they keep it alive? Also no. Next, can they be nil? Strong references can be either optional or non-optional. Weak references must always be optional since they can clear out at any time. Unowned references are never optional because they assume the object is always there. Finally, when do you use them? Use strong by default for your standard object relationships. Use weak specifically to break retained cycles, like in delegates or closure capture lists. And use unowned only when you're 100% certain the target object will outlive the sender. That wraps up our deep dive into Swift memory management and references. Thank you so much for watching. If this helped you level up your iOS development skills or prepare for your next technical interview, please hit that like button and subscribe for more Swift tutorials. Let me know in the comments below what iOS topic you want me to cover next, and I will see you in the next video.